video is going to talk about how to propagate uncertainty when you're measuring melt inclusion vapour bubbles using Raman spectroscopy. So I encourage you to watch some of the previous videos, particularly showing how to get this notebook and the example data off Read the Docs. So you're going to have to install DiodFit if you haven't done so already, so you'd have to uncomment this line. And then we're going to load all our Python information. So what this notebook is doing, it is basically propagating the three sources of uncertainty when you are calculating the equivalent amount of CO2 that's held in the vapour bubble that would exist if you were to dissolve that vapour bubble back into the glass. Okay, so you would be adding that ppm CO2 back into what you've measured by FTIR or SIMS. And we do that by making a Monte Carlo simulation. So we're basically defining a distribution of each input variable. So we're just going to do a simple example for a single melt inclusion here to talk you through those three main sources of uncertainty. So you are basically adding that vapour bubble back in by a mass balance. And the way this mass balance works is you need to know the volume of the vapour bubble, you need to know the density of CO2 in the vapour bubble, and you need to know the density of the silicate melt. So here we're going to consider a reasonably typical Hawaiian melt inclusion with a 5 volume percent bubble. Now, let's say that you've reconstructed that volume percent using optical methods, so just by measuring the ellipse in a 2D image. That has a large uncertainty associated with it, and Jonathan Tucker has simulated that uncertainty, and a reasonable estimate of that uncertainty is about a 40% uncertainty. So here we're saying a 40% uncertainty, and we believe that uncertainty is distributed normally. Now, if you look at Jonathan Tucker's paper, it's not distributed quite normally, but this is a reasonable approximation given the magnitude of the uncertainty. If you had done micro CT, you could obviously make that error much smaller because it's not going to be 40%, it might be more like 5 or 10%. Second parameter is the vapour bubble density. So this is what you've determined using Raman spectroscopy. And you're going to want to estimate an error on that. This could be from repeated measurements of that bubble, or we do it in DiodFit by looking at the peak fitting error and the error in your drift correction and the error in your densimeter used to convert peak splitting into density. So however you get that value, you can put it as a percentage error. In this case, we're putting it as an absolute error. So the absolute error is 0.01 gram per centimetre cubed, which would be a 50% percentage error. And again, we're saying that we believe that error is distributed normally. You could also have this as a uniformly distributed error, but in this case, normal's better. The density of the silicate melt, chances are you've calculated this from a tool like DensityX, and that tool actually gives you the uncertainty on that. So in this case, the melt density is 2,700 and the error is 80 kilogram per meter cubed. Again, it's an absolute error distributed normally. So now we feed it into this function. What this function does is for each input variable, it makes a distribution which is centered on your preferred value. It has a standard deviation or a spread, depending on whether you've put a normal or a uniform uncertainty, defined by the error parameters that you've given it. And then what it does is it basically multiplies those different distributions together. In this case, we've asked it to make 1,000 duplicates. And that gives you an error distribution for your resulting CO2 content. So let's just run this, and you can see that this is being stored in a data frame called test distribution. So what are the columns? So this left-hand column, this is showing the equivalent amount of CO2 in the melt for the Monte Carlo simulation. So here we're only printing the first 5 rows, but if we get rid of this, you'll see there are actually 1,000 rows, so this is all 1,000 simulations. So one simulation pulling from the density of the melt, the bubble volume and the bubble density gives you 785 ppm. Another gives you 62 ppm. So you can see there's 1,000 different possible options. This column shows the preferred CO2 in the melt using just those input parameters, so the 5 volume percent and the density of the two things. If you just want to see where that comes from, we have just written out here the basic mass balance. It's basically the bubble density times the volume percent divided by the melt density, and you can see that gives 370. So 370 is the value that people would typically have used for this, and then that left-hand column is actually propagating the uncertainty fully. Then we have the input parameters. So we wanted 5 volume percent with a 40% noise. So the first simulation, the bubble volume percent was 6.8. The next one, 3, 7, 10, etc. Same for the CO2 density. This is that input with that noise added. And same for the melt density. And you can see all of your input parameters are in here. So you can see what you selected, that you selected a normal distribution and a percentage error, etc. So let's plot what these look like. So you can see here on the first plot, we are plotting the volume percent of the bubble with the noise added. So this is your distribution of bubble volumes that the simulation is using. So you can see it's centered on 5, and then you have that standard deviation of 40%. This is your input parameter for the melt density, and this is your input parameter for the bubble density. And when you propagate those together into the equivalent amount of CO2 in the melt held in the vapor bubble, you get this distribution. So you can see that you can basically define a preferred value, and that is actually, that's 370 ppm. And then you can calculate a standard deviation, and that is basically the error that we're going to be using. So we're not going to be using the mean of the distribution necessarily, because this can depend on your n. What we're going to do is we're going to take the preferred value for the CO2 using the values that you gave it, so that's that 370 value, and then we're going to use the standard deviation, so the distance between these dashed lines. Okay, so that's one vapor bubble, but obviously you're not going to want to have to do this manually. So we're going to load in some data. So this is data from my 2021 paper looking at the 2018 eruption of Kilauea, which had beautiful vapor bubbles. And you can see this is a reasonably typical spreadsheet. What we have here is we have the melt density, this is grams per centimetre cubed. This was calculated using density X. We have an error on it. We have the volume percent of the bubble. We have the CO2 density I measured by Raman spectroscopy, and then we have an error on that CO2 density, and that is from repeated measurements of the same bubble. Okay, so we're going to load in that data, and it doesn't matter what you call your column headings. It's how you feed them into the next function that is what matters. So this function is very, very similar to that function above. The only difference is this function up here is designed for a single sample, which is why it has this ind here, so ind for individual. And this function basically uses that smaller function to do it for every single row that you feed it. So the first thing you're going to tell it is the sample ID. So you can see in my data frame I loaded in, I called that data frame sample. You're going to say how many duplicates you want. So I want 1,000 duplicates for every single one. That means it's kind of a toss-up. The more duplicates you get, the more reliable your standard error is, but it takes longer computationally. You're going to tell it the volume percent of your bubble. So that's this column here. You're going to tell it your CO2 density that you measured. So that's this column. You're going to tell it your melt density. I have to times this by 1,000 to get the units into kilogram per meter cubed. Here I'm using a 50% error on the bubble volume. I could change that to 40. It really doesn't matter. I was just being very conservative when I did this study. Again, and then I'm telling it the distribution. So I want a percentage error, I want it normally distributed. This is my error on my CO2 density, so on and so forth. So this is basically the same parameters we defined above, but largely reading from the spreadsheet. So we can run this, and it just tells you what sample it's working on. And what this outputs is it outputs 3 things. So what average does is for each of those 1,000 simulations, it basically returns 1 row. So that row has the preferred value, not doing the Monte Carlo simulation. It has the mean of the Monte Carlo simulation, it has the median of the Monte Carlo simulation, and it has the standard deviation of the Monte Carlo simulation. If you wanted to look at all 1,000 simulations for every single one, you could also do that. So you can see here, this test dist, this has that first melt inclusion LL8613B 1,000 times, and then the next melt inclusion, and so on, so forth. So if you wanted to look at the individual inputs, that would be the way to do it. And what we've done here is we've just returned the plot for one of these. And this is basically so that you can have a look and check that, you've given what you think is a reasonable range. So I would look at this and say, do I think it's reasonable that my melt density was between 2,650 and 2,800? 300 approximately. And I think, yeah, that is reasonable. So now you've got this data, what might you want to do with it? Well, when you go and calculate saturation pressures using a tool like VisiCal, you might want to, first of all, take the preferred value of CO2, okay? So then you would add that to your SIMS data or your FTIR data. You would correct for processes like post-entrapment crystallization, and you would run the saturation pressures for that mean value. You then might want to take your SIMS data and you might want to add, in addition to adding in this CO2 in the bubble, adding the standard deviation. And that would give you an upper limit of the CO2. So you'd basically be adding 340-ish rather than 220. You then might want to run the saturation pressures again, minusing that standard deviation. And then you basically have 3 saturation pressures for each melt inclusion. You have the mean and you have the standard deviation. You might want to propagate other sources of uncertainty like the CO2 in the SIMS as well, and you can do that using quadrature, or you could do your own Monte Carlo simulation for this.